In the dynamic economic model, there is another approach is Almon approach. So in the Almond approach, yt, it's a dependent variable. It depends upon alpha plus beta naught xt. There is some explanatory variable, not only current period but also some previous period. Yt depends not only xt but also the previous periods of x value. Yt it's equal to alpha plus beta naught xt plus beta 1 xt minus 1 plus beta 2 xt minus 2 plus up to beta k xt minus k plus ut. Here ut it's the error term. In the next line, yt it's equal to alpha plus sum of I equal to 0 to k beta I xt minus I plus ut. This is equation 2. Following a theorem in maths known as Weierstrass theorem says that states that beta I can be approximated by a suitable degree polynomial in I. The length of the lag, broadly speaking, the theorem states that a finite closed interval. Obviously, because sum of I value it's 0 to k. Any continuous function may be approximated by polynomial uniformly by a polynomial of suitable degree. Beta I is equal to alpha naught plus alpha 1 I plus alpha 2 I square. This is a second degree polynomial. Equation number 3. This line. Second degree polynomial. I has a closed interval. I has a closed interval that is in between 0 and k, and I is integer. I is integer, and a third degree polynomial can be considered that beta I equal to alpha naught plus alpha 1 I plus alpha 2 I square plus alpha 3 I cube. This is a third degree polynomial. And the equation number 4. And the mth degree polynomial is mth degree polynomial. There is mth degree polynomial that is alpha naught plus alpha 1 I plus alpha 2 I square plus alpha 3 I cube plus alpha 4 I power 4 plus up to alpha m I power m. That can be written as mth degree polynomial. It's beta I it's equal to alpha naught plus alpha 1 I plus alpha this is equation number 5. It is also called the mth degree polynomial. Here m is less than k. M is a period of lag and m is degree of polynomial. M, what is m? M is degree of polynomial. Degree of polynomial. What is k? K is the Period of lag. How many lag is there? If we assume second degree polynomial, then we can write the model as in this way: yt equal to alpha plus sum of I equal to 0 to k beta I xt minus I plus ut. This is second degree polynomial. That is why we consider it in next line, that is equal to alpha plus sum of I equal to 0 to k beta naught alpha naught plus alpha 1 I plus alpha 2 I square x t minus 1 is there. So basically beta I second degree polynomial considered. That is why second degree polynomial beta I is alpha naught plus alpha 1 I plus alpha 2 I square. The other term is that ut is there, um, plus ut minus 1. So in the next line yt is equal to alpha plus alpha naught. So we just break down the uh, bracket term, and we can write it as in this way: yt it's equal to alpha plus alpha naught sum of I equal to 0 to k xt minus 1 plus alpha 1 sum of I equal to 0 to k xt minus 1 plus alpha x2 sum of I equal to 0 to k I square x t minus 1 plus ut. And we can consider that z in the next page also. We can show that z0 t it's equal to, so z0 t equal to sum of I equal to 1 to k x t minus 1. It is also can write x from this, from here and from here, that z0 t it's equal to x t minus 0 plus x t minus 1 plus x t minus 2 plus up to plus x t minus k. If z1 t it's equal to sum of I equal to 0 to k I into x t minus I, we can write it as 0 into xt minus 0 plus 1 into xt minus 1 plus 2 into xt minus 2 plus up to k into xt minus k. And the last is z2t. It is a 2 degree polynomial. That is why sum of I equal to 0 to k I square into xt minus 1. So it can write it 0 square x t minus 0 I square x 1 square x t minus 1 plus 2 square x t minus 2 plus k square into x t minus k. In the Almon scheme, yt is regressed on the contribute constraint variable. uh, so uh, Almon approach, yt regressed on the constraint variable z0t, z1t, z2t, not on the original x variable. Here, in this case, ut all retained, all the classical linear regression we can apply Welles procedure. The estimates of alpha naught, alpha 1, alpha 2 thus obtained, we have all the desirable property provide the stochastic disturbance term. This satisfies assumption of classical linear regression model. Once we get the value, if we get the value, so if we once get the value of alpha naught hat, alpha 1 hat, alpha 2 hat, estimated alpha value, we will be able to derive values of beta naught hat equal to alpha naught hat. Beta 1 hat is equal to alpha naught hat plus alpha 1 hat plus alpha 2 hat. beta 2 hat equal to alpha naught hat plus 2 alpha 1 hat plus 4 alpha 2 hat. Similarly, beta k hat is equal to alpha naught hat plus k alpha 1 hat plus k square alpha 2 hat plus dot 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 plus. So how can we get the value of mm, beta naught hat, beta 1 hat, beta 2 hat, beta 3 hat, beta k hat? We can show that. So if I is equal to 0, so beta I, we know this is a 2 degree second degree polynomial, so beta I equal to alpha naught plus I alpha 1 plus I square alpha 2. If though I is equal to 0, so beta 0 or beta naught is equal to alpha naught plus 0 into alpha 1 plus 0 square into alpha 2. So ultimately we get beta naught is equal to alpha naught. Similarly, if I is equal to 2, beta 2 is equal to alpha naught plus 2 into alpha 1 plus 4 into alpha 2, and if I equal to k, so beta k is equal to alpha naught plus k alpha 1 plus k square alpha 2. In this way, uh, we get the value, and the estimated value, that is alpha naught hat, alpha 1 hat, alpha 2 hat, and alpha k hat. So now, from where the beta 1 hat, beta 2 hat, and beta k hat is getting, this is now clear. Here, the two important feature of the Almon approach is length of the lag must be specified. What will be the lag length? That is must be specified. And here the degree of the polynomial will always be less than the period of the leg. That is considered in the second important feature, that is considered here, that the having specified k the lag length, we must also specify the degree of polynomial m. Generally, the degree of the polynomial m should be at least less than the number of degree of polynomial. And some advantage of the quick model, they are considered the three advantage of the quick model. The three advantage of the Almond. There is a comparison with the Quake and Almond approach. That is, Almond approach or Almond method. It's incorporative. It is a flexible method. There is a variable lag structure. Incorporative variable lag structure is there in the Almond approach, but Quake structure is somewhat rigid. Here, beta can be positive, beta can be negative, but quick approach, beta 1, beta 2, beta 3 are all positive. This is a rigid model. In this model, there is no lagged dependent variable as the explanatory variable in case of Almond approach. This is the second approach. No lag dependent variable as the explanatory variable. There is no lag dependent variable. And finally, uh, there is sufficiently low degree of polynomial can be fitted. The number of coefficient can be estimated. It's considerably smaller than the original number. And also some problem in this model is there, that is the problem of this model is the degree of polynomial as well as the lag length is subjective. Here, z variable are likely to exceed its multicollinearity. There may be the problem of multicollinearity arise in the z variable. It is difficult to capture long tail lag distribution. This problem can be solved by the piecewise polynomial. Problem of choosing the lag length, that is k, should be such that a model with a particular value k should take the adjusted r square for a different value of k. And the last problem of this approach is problem of choosing the degree of polynomial can be done by the trial. The length of k is correctly specified, then we first choose the significantly high degree of polynomial and then check whether the coefficients are significant or not. Then by dropping the higher term sequentially, the proper way of testing is to test a highest degree polynomial and go beyond until coefficients are rejected.